in Europe. They used to exist in our ports back in the late 19th century. This is the day that the Chinese fleet can actually go out and fish in last year. And you can see it's a huge effort that's attacking our seas, but also providing the food that people need. So while fishing is the biggest historical impact on our seas, and it's still important in coastal areas, there's also multiple pressures nowadays of climate change, ocean acidification, coastal development for tourism, so people can go and see these beautiful places, building hotels, sea level rise, pollution, and we hear much more about these tonight. The coastal systems, though, are essential for people's livelihood, and we mustn't forget that people are part of these systems. It's where people interact with the sea, and it's also probably where humanity started. Most of the earliest civilizations were connected to the sea or to rivers or to estuaries. So how can we move forward with the sustainable seas and sustainable communities? We have 3 talks tonight from leading people working in the forefront of marine conservation in the tropics, with Earthwatch, but with diverse topics and different locations. We'll then have a question and answer session for all, so please keep any questions till then and we can deal with them. So to start us off, it's with great pleasure that I introduce Professor Mark Huxham. Mark is Director of Academic Strategy at Napier University in Edinburgh, the founding director of the charity, the Association of Coastal Ecosystem Services, and leader of the Earthwatch community-based mangrove research and conservation project in Kenya. Mark Huxham.
Thank you, Martin. In this globalized world, which is media saturated, much of nature has lost its mystery. But for me, one habitat remains almost impossibly exotic. It's a place where the normal rules of biology appear not to apply. This is a place where you can see crabs foraging like caterpillars up in the foliage. You can watch fish nesting amongst tree trunks. You can see tigers swimming about like seals, and you can see forests sprout in the ocean. The world's mangrove forests are not only biologically unique, they're also uniquely important to human beings. They provide food and fuel. They filter out pollutants and silt. They protect the coral reefs that you're going to be hearing much more about shortly. They protect coastlines from erosion and tsunamis. And they capture and store billions of tons of climate-wrecking carbon. So what I'd like to do tonight is to spend a little bit of time describing the world's first community-based mangrove conservation project, which is funded by carbon credits. And this is a project that's developed from Earthwatch work in southern Kenya over more than the last 10 years. So I want to describe some of the science that underpins this work. But before I do that, I want to consider a paradox. Imagine that you've inherited from your parents a beautifully decorated house that's brilliantly designed to protect you from the elements, that's in a fantastic coastal location. It contributes to your income, and it's something that your ancestors have always revered. Wouldn't you do what you could to protect that house and to pass it on in good condition to your own children? So if mangroves are as important as I've just described, if people depend on them as much as I've suggested, why is it that around the world these forest ecosystems are being destroyed and degraded? And I think to answer that question, we have to think a little bit about dependency and types of human dependency. When I broke my leg showing off to a girlfriend rock climbing, I became dependent on crutches. And that was dependence from necessity. And that kind of dependence speaks the language of sweat, by which I mean it's really hard work and it's really obvious. You can't deny it. But it was temporary dependence, my leg recovered, and it was local. It affected me and not very many other people. And some of the ways in which people depend on mangrove forests reflect that kind of dependency. By analogy, they rely on mangrove forests as a kind of bio-crutch. This is perhaps the best example of that dependence. This is Fuelwood. This woman here lives in Gazi village in southern Kenya, and like 76% of the other people in that village, she relies on mangrove fuel wood for her domestic use. And she uses on average just over 2 kilograms of that wood a day. Collecting it is really hard work. The women, it's 96% of the people who do the collecting are women. The women collect it in these bundles and they burn it on, frankly, very primitive and inefficient open fires. This use of the mangroves is not sustainable. It may have been in the past, but with population growth, it's no longer sustainable. It's not good for people. It's a dependence from which people need to be liberated. And if you doubt that, then look at the relationship between people's wealth and their dependence on mangrove fuel wood. These are data from across the globe where people have looked at case studies of communities living adjacent to these forests and measured the percentage of households in these communities that use fuel wood. Up here, there's Kenya, there's Cameroon. You can see very, very heavy dependence on fuel wood. By the time we get to Mexico, along this axis of GDP per capita, a rough axis of people's wealth, nobody in Mexico uses mangrove wood for fuel. And that's because they've got better options. They don't have to go collecting fuel wood from the mangroves. So some dependencies we want to liberate people from because they're not good for the people and they're not good for the ecosystems. But other kinds of dependencies are quite different. These are dependencies from birthright. I'm fortunate to live in Scotland, where we have the best tap water in the world. We've got a lot of water in Scotland, and like most people, I hardly give it a second thought. I take it almost entirely for granted. If I do think about tap water, then I start to speak the language of science. It's a technical language of catchments and porosity and groundwater flows and so on. It's a permanent form of dependence. It makes no sense to think of liberating people from their dependence on water. And of course, it's not local, it's global. So one of the challenges that we had in our project, and I think many conservation projects face, is to find the right language to speak about dependence. We need a language which doesn't just speak in the language of sweat, because that language is not understood by the rich and powerful. They don't collect fuel wood. But we also really don't want to speak, not all the time, in the language of science. It's too technical and people don't understand it. The language that we speak when we need to in this project is the language of money. The language of money is understood in the corridors of power, but it's also, you can translate that language, that abstract language, into real hard cash, which makes a difference for some of the poorest people in the world. We had to find an ecosystem service, a dependency, if you like, that is provided by mangrove forests that we could translate into that language that could be understood. And the one that we worked with, most of all, is carbon. And the reasons we work with carbon is partly because it's a fascinating part of the ecological story of mangroves, but also because there's a multi-million-pound international market that trades in carbon. So we wanted to use some of that money to help local people in Kenya. So I'm going to divert for a moment into climate change and a brief discussion of, first of all, why we're interested in carbon at all, and secondly, why that's particularly relevant to mangroves. So human beings, back in 2009, these data are slightly out of date now, human beings were responsible for almost 10 billion tons of carbon being released into the atmosphere every year. And when that carbon goes up into the atmosphere, something very interesting and very important happens to it. 57% of that carbon disappears from the atmosphere. There's a magic disappearing trick. This is vital for us because we know how serious climate change is at the moment. Without this disappearing trick, climate change would be running more than twice as fast. So what happens to that carbon? Well, slightly more than half of that 57%, about 2.6 billion tons, goes into terrestrial ecosystems. It's sopped up by forests in particular. The other half, or slightly under half, 2.2 billion tons, is absorbed into the ocean. And I want to follow up and think about where that absorption is going in this next slide. So what you can see here is 4 important key marine habitats. This is the deep ocean. This is coastal shelf. This is estuaries. And this is vegetated coastal habitats, so mangroves, salt marshes, and seagrasses. And one approach to this problem that people certainly took maybe 20 years ago was just to look at the spatial extent of these habitats. So if we want to know which are the important habitats in the ocean for all sorts of ecological functioning, including carbon sequestration, then let's just look at their spatial extent. And if we do that, this is the picture that emerges. More than 80% of the ocean is deep ocean, it's classified as deep ocean. About 14% are coastal shelves. There are the estuaries, just hanging in there at 0.5%. The vegetated coastal areas has disappeared. That's down at 0.04% of spatial extent. So if we were guided by that, then we would simply ignore these coastal habitats. But to do that would be making a very serious mistake. And it's something that we've discovered really over the last 20 years, and partly with the help of Earthwatch support. When we look at the percentage efficiency of these habitats in capturing and storing carbon, a very different picture emerges. So now you can see that mangroves and vegetated ecosystems are about 22 to 24 times more efficient per unit area than the deep ocean. So if you're interested in bang for bucks, if you're interested in value per unit area of investing in marine ecosystems for carbon storage, then you really want to look at these coastal ecosystems. Why is it that mangroves are so good at trapping carbon? One of the other things that we've discovered in the last decade really, is that these ecosystems have a very clever trick when they're faced with sea level rise. They stand right at the interface of the sea and the land, and because oceans across the world are rising at average about 3 millimeters a year, there was great concern, there still is great concern, that most of these mangroves will simply drown. Although they can tolerate some seawater, if they drop below mid-tide level, then their roots can't get sufficient oxygen and they die. In the past, in previous geological ages, we know mangroves have tracked sea level, so they've regressed inland. But most of the mangrove forests in the world don't have that option anymore, because behind the forests are coastal developments, roads, agriculture, and other things. So does that mean that mangroves are doomed to drown? Well, with luck, no, it doesn't. So as the sea level rises, the sea brings nutrients to these ecosystems, and they tend to be very, very nutrient limited. They get by on astonishingly low levels of nitrogen. What that does is stimulate root growth in the mangroves. So first of all, above ground root growth, and then secondly, below ground root growth. And that below ground root growth literally pushes up the surface of the land. The above ground root growth captures sediments and particles, carbon-rich particles, and the net result of both of those processes is that the mangrove forests build land. They're land builders. They can keep up with sea level rise. If you have a healthy mangrove forest with plenty of support, some nutrients and some sediment, that mangrove forest can keep up with sea level rise. So if you're on a tropical shore and you're faced with problems from sea level rise, one of the best things you can have in front of you is a mangrove forest. So we end up with this very, very interesting, very carbon-rich matrix of organic material in these forests, much of it below ground. And what you can see here is a complex mix of there's a bit of seagrass that's come in from the sea, carbon being washed in from the sea, all sorts of sediment that's come down from the rivers, and all sorts of material that's leaching out of these living roots. And then the roots themselves, of course, die and end up deposited below ground. And to look at a mangrove forest and measure it as carbon that you can see above ground is very misleading, because the proportion of carbon in these forests above and below ground looks something like this. More than 90% of the carbon is buried below the roots. So in our site in Kenya, we've spent a lot of time digging holes. It's always one of the favorite tasks for our Earthwatch volunteers. But that task has been very important because we've discovered some salient facts. We've discovered that we can go down 3 meters. That's as far as we can safely go, and we haven't hit bedrock. So there's an awful lot of carbon down there, and some of those plots are approaching 3,000 tons of carbon per hectare. That's an extraordinary density of carbon. It really means that we need to restore these forests, but perhaps even more importantly, we mustn't allow all that carbon currently locked away and stored for tens of thousands of years, we mustn't allow that carbon back into the atmosphere. So one of the questions that we've been able to answer with Earthwatch support is, what happens when you start damaging the forest to that precious carbon, to that carbon locked below ground? And if you're going to manage these forests, if you're going to, for example, have rotation forestry, can we give some advice on that management? Well, for the first time, we had a Kenyan PhD student who conducted a large-scale field experiment in the forest, which involved experimentally removing plots of trees. These were 12 by 12 meter plots, so not that big, but still a lot of work in the forest for Joseph. And what he found by measuring fluxes of carbon from those plots was that we lost getting on for 30 tons of CO2 per year from the forest floor, and we saw very, very significant subsidence. The forest floor was no longer rising, it was sinking. And that was much more rapid and much more alarming than we'd expected. In fact, you can compare those kinds of rates with values that people have recorded following hurricanes and tsunamis. So it turns out that at least some of these sites, some of these forests are really quite sensitive to disturbance, and we can advise managers when they're thinking of cutting areas of the forest to avoid those very sensitive areas. What can we do with all of this scientific information and this knowledge? Well, we've worked to develop a carbon sequestration and a carbon credit sale project called Mikoko Pamoja, and that stands for Mangroves Together in Swahili. And that project does three very important things. First of all, it's involved in planting mangroves. So one of the things that we discovered was that areas that have been cleared of these trees 40 years ago when we started working there and had seen no natural regeneration at all, those areas could be brought back to life, but you had to work very hard at it. And the way you do it is you foster trees in nurseries, safe nurseries like this, and then you transplant them to these tough areas. And you can expect large mortalities, but eventually the trees can survive and help restore those ecosystems. So we plant about 4,000 mangroves every year there. Second thing we do is spend a lot of time on education. So there are two primary schools in the area and two secondary schools as well. We work very closely with the children from those schools. Earthwatch volunteers and scientists have been responsible for sponsoring now more than 26 children through school. And in fact, one of the first children that we supported last year graduated from university. So we've seen Alfred through primary, secondary, and tertiary education now. So we work very closely with schools, primary level, secondary level, and all the way through to PhDs, helping to communicate the message of the importance of mangroves. The carbon money that we're able to raise is run, all of this project is run by volunteers, and about 60% of the money we raise at the moment goes into helping to run the project. There's one person who's paid on the project, and that's our local village community liaison officer, who gets paid $3,000 a year. So it's small money, but what's left over from that, about 40% goes into a community fund, and the decisions on how to spend that money are taken entirely by local people through democratic processes. And so last year, local people decided to spend it on new school buildings, school roofs, and school books. This is one of the school buildings that we were able to fund with some of our early work. This year, the chairman of Mikoko Pamoja Community Organization contacted me last week and said, we'd like to invest in new wells in one of our neighboring villages. This is an area where there's a real problem with salinization, where women have to walk for more than 2 kilometers at the moment to get water. So people can see really concrete benefits from getting engaged in conserving the forest. So many people have contributed to and benefited from this work. We've had more than 250 Earthwatch volunteers working with us in Ghazi from more than 40 different countries. working with a whole range of different universities, and of course with Kenyan researchers all the time and the Kenyan government. Because this work is recognized by the Kenyan government as an example of good practice in climate change adaptation, and because it's also recognized by the United Nations, it's achieved quite a high profile now, and we're often being contacted by other communities along East Africa to say, look, can you come and help us establish similar schemes in our mangroves? And our answer to that is, yes, we'd love to do that. We're looking forward to continuing support from Earthwatch to help us to do just that. And our intention is to help liberate people from those dependencies which are there for necessity, and help celebrate those dependencies which are birthright. They're birthright, like the mangroves. Thank you.
Thank you, Mark. Professor Jennifer Smith is an associate professor in marine ecology and conservation at Scripps Institution of Oceanography in California. She's focused on understanding how humans impact marine ecosystems. Jennifer is leading a new Earthwatch project looking at the ecological impact of seaweed farming in Indonesia and the susceptibility of seaweed farms to environmental change. Jennifer Smith.
Good evening. Thank you all for coming. And I'd like to pay a special thanks to Earthwatch for inviting me to speak here with all of you tonight. So I'm going to start off my talk giving you an overview of the research that I do and the work that my lab does at Scripps Institution of Oceanography. And then I'm going to end with a prelude into the work that we're hoping to launch with Earthwatch this year. So for all of you who have been fortunate enough to go scuba diving or snorkeling on coral reefs, I'm sure you share my passion and enthusiasm for these marine ecosystems. Coral reefs are truly one of the most spectacular ecosystems on the planet. They're home to many different species, and they're unique in that the coral reef ecosystem is built by animals. So these are the corals that are building the foundation of the ecosystem. Most other ecosystems around the planet are built by plants, and so they are truly a unique ecosystem. In addition to being incredibly beautiful and spectacular and enjoyable to visit, they also provide numerous important ecosystem goods and services to communities around the world. They're first and foremost known for their ability to support a huge amount of biodiversity. So despite the fact that coral reefs occupy an area of the planet that is about the size of the country of France, they're home to about 25% of the ocean's marine species. So they are the single most biodiverse ecosystem in the ocean. Coral reefs are also important because they provide physical protection to coastlines around the world, specifically in the tropics. This is because corals are actively building reefs. They're laying down calcium carbonate or limestone underneath their soft tissue. And as they do that, they grow up towards the sun and they create these massive barriers or geologic features that you can see from space. And these geologic features protect the coastlines from the battering forces of wave energy, storms, hurricanes, tsunamis, cyclones, and all other kinds of large storm events. They're also important for generating a large amount of revenue. So many tourists, many people like you and I are willing to pay money to visit coral reefs and to interact with these spectacular ecosystems. They're also important from a fisheries perspective. So many tropical island nations around the world are dependent entirely on reef-associated fisheries. These are fish that are derived from the reef ecosystem and not pelagic species like tuna. This is, of course, problematic when you consider many of the species shown here, which are parrotfish, which happen to be very important for maintaining reef health, and I'll talk more about that in a minute. So all of these ecosystem goods and services are entirely attributed to the corals, these animals that build these fantastic ecosystems. Corals are very simple animals. They resemble sea anemones, and through the process of cloning or budding, they create a colony. So this is many coral polyps. They're all connected together. They share resources, and over time, they deposit calcium carbonate underneath this very thin veneer of soft tissue, and they create these massive geologic features. So this is one coral colony. It's probably 500 or 1,000 years old, and over time, it's built this complex structure. And through the incredible diversity of corals that exist on the planet, we end up having coral reef ecosystems that are dominated, that these corals create many different diverse habitats. And so you have branching corals and plating corals, and this provides the habitat and shelter for all of the species that live on the coral reef. You've all probably familiar with the fact that coral reefs are undergoing a global crisis. It's estimated that about 20% of the world's coral reefs have already been lost, and many more are in immediate danger. These losses are occurring largely as a result of anthropogenic or human-derived causes, occurring at both local and global scales. And what I mean when I say we've lost coral reefs, we see these coral-dominated environments, such as shown here, where the landscape is dominated by these reef-building calcium carbonate depositing organisms that are creating that geologic feature that we can see from space, undergo a phase shift to dominance by fleshy organisms. So you can see that this environment looks much different and does not no longer has the same ecosystem services that a coral-dominated reef would have. We've seen these phase shifts around the world, in the Pacific, in the Caribbean, in the Indian Ocean, and basically what ends up happening is that we're on the slippery slope to slime. So once these reefs become dominated by seaweeds, it becomes very difficult to reverse them or to do restoration to bring them back. So this encompasses a large amount of the work that my lab at Scripps Institution of Oceanography is focused on. We're primarily interested in determining the effects of various anthropogenic disturbances on coral reefs, understanding how humans interact with reefs and how that changes the structure of reefs. We're interested in understanding how reefs look or how they exist in the absence of humans. And to do this, we travel to very remote locations in the middle of the Pacific that have never had local human populations. And this provides a baseline for us to better evaluate the potential for these reef ecosystems today. And then all of this work is ultimately feeding into working with local communities to develop better, more effective, scientifically sound conservation strategies to ensure that these ecosystems persist for future generations. So I'll start with the first, looking at various anthropogenic disturbances on coral reefs. So many different types of impacts can affect the structure of reef ecosystems: overfishing, nutrient pollution, sedimentation, the introduction of exotic species, and I'll just focus on the first two here today. And these are all issues because they occur at a local scale. Management action at a local scale can help to mitigate or to reverse these impacts. In terms of overfishing, humans have derived a variety of different fishing practices to remove fish from marine ecosystems. And for the case of coral reefs, many of these fishing practices are destructive, such as dynamite fishing, cyanide fishing, and a whole variety of techniques which kind of wholesale remove all species from the reef ecosystem. So they're not necessarily targeting a specific fishery. And that becomes, again, specifically problematic for species that we know have really important ecosystem services. Specifically, I have been interested in the effects of herbivores. So herbivores are the species of fish that consume seaweeds that compete with corals. And so to do that, we construct a variety of experiments where we can remove herbivores from the reef ecosystem and look at how the benthic community, the corals and the algae, change over time. And experiment after experiment, we have shown that basically when you remove herbivores, you get more seaweed. So this is basically like what would happen if you stopped mowing your lawn. You would get weeds taking over your lawn. Well, the same thing happens on a coral reef. And these species are particularly important, specifically things like surgeonfish, parrotfish, and sea urchins. These are all the lawnmowers of the coral reef. And so these species are very important to maintain and to protect on coral reefs. However, we've seen globally that these species are actually highly overfished. Through a recent global synthesis looking at the fisheries or the population of herbivores around the globe, across, again, the Pacific, the Caribbean, and the Indian Oceans, we've seen that in fisheries accessible areas in red versus areas that are closed to fishing, we see basically almost a doubling of the amount of herbivore biomass, or the mass of these herbivorous fish species in areas that are closed to fishing. So these fish are globally overfished, and yet we know they're incredibly important for maintaining reef health. And so this has very important implications for the development of protected areas. We should consider protecting some of these species that we know we need to maintain for those ecosystem services to allow corals to be the ecological dominant. The work that I've done in this area has helped to establish one of the world's first herbivore fisheries management areas. This is an area on the island of Maui in the Hawaiian Islands. This protected area went into place in 2009, and since its protection, we've seen a dramatic, albeit somewhat slow, but an increase in the herbivore populations at this site. In addition, we're seeing some evidence of the benthic community becoming more healthy. So we're getting an increase in those calcifying organisms and a decrease in the fleshy algae. So we really believe that this is a good way, a successful management option for coral reef ecosystems. We're not saying protect all fish species, and we know that's unpractical because people need to eat, but we at least need to protect those species that we know have very important ecosystem services, such as their ability to remove the weeds from the reef. So thinking about other local impacts, such as nutrient pollution, this is the addition of things like nitrogen and phosphorus to coral reef ecosystems. We do this in a variety of ways, through agriculture, through sewage runoff, through landscaping and golf courses, and through general runoff through activities that occur on land. All of these activities add nitrogen and phosphorus into the coral reef environment. This is problematic because coral reefs are what is known as oligotrophic, which is low in nutrients. You go to a coral reef, the first thing you notice is how beautifully clear the water is, and that's because there's very little nitrogen and phosphorus in the water column. So when we add these nutrients, nitrogen and phosphorus, what we're essentially doing is fertilizing the reef, which ends up fertilizing, again, the weeds. So if you fertilize your garden and you're not out there weeding all of those fast-growing species, again, you're going to have weeds take over that environment. And so we see the same thing on a coral reef. Numerous studies have that I've been conducting over the years have shown that when you put a lot of nutrients in the water, you can get these massive seaweed blooms. This work is specifically, again, taken place on the island of Maui, where I did a lot of my PhD research. And we noticed that in 3 locations around the island, there were these large-scale seaweed blooms, and these happened to be occurring directly downstream from the 3 urban sewage treatment facilities on the island. And whether this is coincidence or not, I've spent several years working on this issue. And basically, these sewage treatment facilities are injecting hundreds of or millions of gallons of secondarily treated sewage into the ground every day. And the island is made of basalt, or porous rock. And so the sewage is essentially leaking through the rock and emerging through the reef. Over years of study, we've been able to show that this is actually having a negative impact on the environment, that we've been able to connect the sewage to the reef. And this has resulted in a large lawsuit, which has been going on for years and is finally going to close at the end of the summer. So basically, we've been able to show that the wastewater is endangering water quality. They've violated the Clean Water Act, and so now we're in the penalty phase. So this is a case where years and years of research is finally going into hopefully making a change for improving water quality on this island. Okay, so now I'm going to shift gears and talk about some of the global causes of reef loss. And again, the causes are many, and I'm not going to talk about all of them, but I will focus on one, which is ocean acidification, which is a bit of a theme for a lot of our research, a lot of the scientists that are here tonight. So these issues are things that are occurring on a much larger scale, global, in fact. And ocean acidification is basically the result of the burning of fossil fuels, which releases a lot of CO2 into the atmosphere. We know that a lot of that CO2 gets absorbed by the ocean. And once it enters the ocean, the chemistry of the ocean changes. And basically what you need to know is that the water becomes slightly more acidic, and also we lose this guy, the carbonate ion, which is what all organisms that build limestone, calcium carbonate is what limestone is, that becomes more limiting. And so we believe ocean acidification is going to be particularly problematic for all of those species that build shells and skeletons. So things like corals, mussels, clams, oysters, anything that has a hard shell, it's going to be much more difficult and potentially impossible for them to maintain their reef building or their calcium carbonate deposition in the future. So my lab has been focusing on addressing this question by bubbling CO2 into little aquaria and looking at the response of a variety of both calcifying and non-calcifying species to elevated CO2. We're really interested in being able to see if we can determine how reef communities in particular are going to shift in the future as the oceans become more acidic. What we've been able to show, just in summary, is that many of the reef-building species, whether it be corals or coral and algae or other important calcifiers, are generally negatively affected by ocean acidification, while some of the fleshy species, which act in a more bioerosive capacity, are actually positively affected by ocean acidification. And this is because things like fleshy algae or seaweeds actually use CO2 for photosynthesis. So they take up CO2 all day long during the process of photosynthesis, and that actually raises the pH. And so while the calcifiers are negatively affected, the fleshy species are positively affected, and that suggests that in the future, we may see reef communities shifting from being these calcium carbonate, dominating reef building communities to ones that are actually dissolving or eroding away. Of course, this will be determined by whether or not these species can acclimate or adapt over time. So these are all based on short-term experiments, and also determined on whether or not we can come up with ways of potentially mitigating this issue. There's a new trend in popular media suggesting that seaweeds may actually be able to mitigate the negative effects of ocean acidification on reef-building organisms and other calcifiers. Again, specifically because these seaweeds are taking up CO2 during the daytime, changing the carbonate chemistry in a way that might buffer the negative effects of OA, of ocean acidification. So this is a wide open question and a hot topic in the research arena, so you'll see a lot of future research addressing this issue. So that sums up the work that I do, kind of focusing on anthropogenic disturbances, at least a brief overview. And I'm going to shift now to just briefly mention the work that we do on remote coral reefs. And so we believe it's really important to be able to understand what reefs look like in the absence of people. What did reefs look like 5,000 years ago? And to do this, we can take essentially a virtual time machine back through time by going to some islands that have never had local human populations. Islands that are so remote and virtually inaccessible, to ask some questions, simple questions. What do reefs look like in the absence of people? And is there evidence that these remote reefs are suffering from some of these global change impacts, such as ocean acidification or warming? So to do that, we travel literally to the center of the Pacific Ocean. Here you can see the region outlined here, to places like the Hawaiian Islands, the Mariana Islands, the Line Islands, Kiribati here, the Phoenix Islands, American Samoa. And we have islands that both that are remote, that don't have local human populations, as well as islands that are populated. And so this provides a really nice context for us to be able to compare what reef ecosystems look like with and without people. And just again, to summarize, when we go far, far from local human populations, we find reefs of 5,000 years ago. Basically, these ecosystems are dominated by so much coral, it's nearly impossible to quantify. When we first came back from one of the first cruises we did to this region, many of our colleagues, especially from the Caribbean, did not believe that this existed, or they thought that we just cherry-picked the best site that we could find to show what these places look like. But this is really at an island scale. So these ecosystems serve as really important baselines for coral reefs globally. They allow us to understand what the capacity of these ecosystems are even today, given all of the global impacts that are happening. And that reefs in the absence of local impacts are actually really thriving today. This suggests that potentially management at the local level, by managing some of those local impacts, we might be able to increase the resilience of these systems to global change. So it's basically about like considering building a very healthy patient. You make that patient more able to resist various disturbances that come through. So even though these ecosystems have seen warming events and are still experiencing similar acidification as any other marine ecosystem, they are still thriving. So the work that we've done in the Central Pacific has helped contribute to the establishment of one of the US's largest marine protected areas. This is the Pacific Remote Island Area National Marine Monument that President Bush made just before leaving office. And he actually used some text from one of our publications in the documentation of this new monument, which was very satisfying to know that the science that we're doing is actually really making a difference for helping to build some of these large protected areas. And so having these massive protected areas in the middle of nowhere is certainly important for maintaining those healthy ecosystems. However, it's really not practical to do this for most locations around the planet because people need to eat. So while it is good to set aside some of these really pristine locations, it's also important to move forward and think about how we're going to interact, or how we interact with the marine environment. And so this is why I'm really excited about the future collaboration that we have with Earthwatch, which is specifically looking, kind of encompassing all of the topics that I just discussed. It's looking at the sustainability and impacts of seaweed farming in the tropics. So seaweed farming is a very large industry, specifically for the product carrageenan, which is a cell wall polysaccharide. It's a thickening agent that's used in many different human products, ranging from yogurt to sour cream, whipped cream, coconut milk, almond milk, whatnot. So a whole variety of human products to make that smooth, thick consistency. It's a multi-million-dollar industry, and the seaweed farming industry has really been promoted as being an alternative livelihood to destructive fishing in the tropics. So many people used to be out blowing up the reefs to catch fish. Now they can actually generate money by having a seaweed farm and use that money to purchase food instead of destroying the reefs. This has been a rapidly expanding industry. This shows an aerial view of one area in Indonesia. This is a canoe. You can see a few others along here, so you can just see the magnitude and extent of these farms. Yet there's been very little research on the topic, and so we have no idea what these seaweed farms are doing to the local ecology and or how sustainable they are for the future. So we're interested in investigating a lot of different questions, looking at how these farms affect the local seagrass and coral reef habitats, how overfishing and pollution might affect the productivity of these farms, looking at the vulnerability of the farms to climate change, and looking at the potential for these seaweed farms to buffer adjacent habitats to ocean acidification. So ultimately, we're tying all these themes together in this upcoming project. So we're really excited about beginning this. Again, given the extent and magnitude of these farms, there's really a large amount of information that we just are lacking, and so this is a very exciting new project. So hopefully I've shared with you a variety of different research projects where I've shown that doing science can actually directly change management, or hopefully move things forward. And ultimately, if we want to maintain all of these really important ecosystem services that coral reefs provide, we need to think more creatively and start stepping outside the box of our traditional approaches. So with that, I will thank you. And
I think we need a little brief pause because we've got to switch the hands over. That's it. Great. Thank you. Professor David Smith is a senior lecturer in marine biology at the University of Essex and director of the Coral Reef Research Unit. He serves as a senior advisor to the Institute of Marine Environmental Research in the Aegean Sea. Dave leads an Earthwatch coral reef research project in the Seychelles, which we'll find out more about now. David Smith.
Thank you very much for that introduction. I do have a hard job being a PI for the Seychelles, I do admit that. So thank you very much. I present today with a few colleagues. I can't take all the credit for the hard work. So some of the names are there. And I'm doing this a bit backwards, really, because first of all, I'd like to introduce you to my partners. And it's very important to realize that this project is very much a collaboration between academic institutes, between business, the Mitsubishi Corporation, who very kindly funded our research and provided us with some very enthusiastic and interesting characters over the last 10 years. And of course, this research would not be possible without our partners in the Seychelles, the Marine Parks Authority. I also need to thank my Earthwatch volunteers, about 100 or so over the years, who have really given some added value to our expeditions. So my research approach is one which is a theme of tonight, and that is to actually look at some of the world's biggest problems that we've identified, but really try to focus our attention on finding management solutions for these problems. These management solutions are very much a human element as well as a natural science element, and consequently our research can be divided into the social sciences and the natural sciences, using different approaches. But ultimately, we really want to ask the question of how we can best manage systems against some of the big problems that we face. Conservation is the act of preserving, guarding, and protecting, and again, that act really requires knowledge of what we can protect versus what we actually need. I can't obviously cover everything tonight, so I'm going to sort of not dip my toe into the social science world. I'm going to talk more about the natural sciences, and I will allude to the social science as we go through. So the project rationale, as we've heard from our other speakers tonight, is this big problem of the knowledge of current and future threats to some of the world's most important ecosystems. The other consideration is that at the moment, we currently have no management options for some of these big problems, such as environmental change. So what do we do about these sort of issues? And of course, the need to balance some of the resource use and protection. We have to consider this in the context of degrading environments and an increasing demand. This figure on the right-hand side there shows that over the next 50 or so years, populations are increasing. Fisheries are going down. It's simply the maths don't quite work out. I'm not the first person to realize the sort of magical beauty of coral reefs. This maybe slightly better than average scientist, Alfred Wallace, recognized the importance of reefs back as far as 1869, and his colleague, of course, Charles Darwin, also recognized that these systems were relatively important. And as coral biologists, we like to grab Darwin as our first coral biologist, and he's on our side. Whereas Wallace sort of waxed lyrical about the amazing biodiversity of coral reefs, what Darwin really noticed was that coral reefs represent these amazing physical structures, really complex, and that was the key to their success. Not only do they produce these big physical structures that we've seen some beautiful images, actually I'm very jealous about where Jennifer works, but these big structures are self-building structures. They build the habitat themselves. What a fantastic system. And these drive the high biodiversity, the food productivity, and support about 500 million people around the planet, a number which is going to increase dramatically. We've heard they're under multiple threats. I've got no time to talk about all of these threats, but I point to the one at the very top there, and that's environmental change. And to us, we feel that environmental change is probably the biggest challenge. The others, of course, are challenges, but there are solutions to some of those issues if the political will is there. What we don't have are solutions to the top two, and that is climate change and environmental change on a much shorter term, which I'll come across in a second. That short term, if anyone tuned into the BBC yesterday, would have seen is becoming very topic. One of the biggest threats to coral reefs globally are the short-term shocks that sometimes the world experiences through El Niños and other climatic events. The last big recorded El Niño was actually in 1998, and during that 6 to 8 week period, 16% of the world's coral reefs were killed. And remember how many people depended on these coral reefs for their food. In that number goes up to 90% in some areas, and what's killing these corals is just a slight increase in temperature, maybe just 2 degrees. During that time, the coral, which lives in this beautiful, simple relationship with microscopic algae, which give the coral their color and provide the food and provide the energy to the reefs and build these structures, that pigment and the algae actually disappear, hence the term bleaching. And the model on the right there shows the big push of heated water going through the Indian Ocean. It's quite disturbing that scientists these days, in this year, are predicting that 2050 might see one of the biggest El Ninos in recorded history. So we are really facing some of these challenges. In terms of the long-term effect, that was the short-term chronic hard-hitting effect. We also, of course, have this problem about climate change. Okay, and as Jennifer has mentioned, one of the biggest threats at the moment to us is what we call the evil twin by a scientist, a leader of NOAA, and that's ocean acidification. And I thank Jennifer for going through some of the complicated chemistry, so I don't have to go through too much of that. So let me first start off in part one, and that's managing coral bleaching, managing against these sharp shocks, these increases in seawater temperature that we see probably about every 7 or 8 years. And this is where I take you through a journey from throughout the Seychelles. We first start off with Desroches, an atoll about 240 kilometers south-west of Mahe. From Desroches, we take a quick plane journey over a few years, actually. It's not during the same trip, to the island called Silhouette, a beautiful granitic Jurassic Park-like island, which is just north of Mahe. And from there, we go to this magical island of Curios. And Curios is the focus of much of my research, and I will be talking to you about that later on. But Curios is a marine park. It's a marine park which is effectively managed and is successful. And I want to make that point very clear because it's to the credit of the Seychelles government in protecting that environment. We call this Search for Survivors because throughout these areas, what we've actually done, and thank you to the volunteers who put lots of effort into this, we've looked at 315 different sites around these different islands, 22,000 data points. And what we actually did was ask a really simple question. What was the age structure of corals in these different reef systems? Because if those corals are older than 10 to 15 years, i.e. have been there since the bleaching event in '98, then of course they're tolerant. If they're present, they're obviously there. And what we found was really exciting, actually, that there is a section of the coral community that were much older than the 10 or 15 years and have clearly survived that '98 event. They're the tolerant, and they're the future of coral reefs. Unfortunately, the other part of the equation are those corals that there was no evidence of survival. And unfortunately, these are the corals which are the most physically complex, the branching corals. Now, these support the biodiversity, and that's quite a drastic problem. To back up those field studies, of course, we're not like scientists we never really like to do it the simple way. We carried out a few laboratory experiments, and the green there represents corals going through a rapid environmental change event in the laboratory, and the green flat line represents that there's been no real change to their health during this event. The reds are crashing out, and that supported our theories. Now, what's most exciting about the research that we did here was that, yes, that's the normal, that's what we see, but when we drag our volunteers away from the crystal blue lagoons of Seychelles and put them into the dirty, muddy mangrove, which I admit are very exciting, not always too convincing to some of our volunteers, we see something really exciting. And that is these big sensitive corals that we see, these big branching corals, which are found nowhere else in these optimal environments, do really well in these dark, dingy environments, but very exciting mangrove systems. And what we see when we carried out the experiments, we see an uplift. Rather than these corals dying out very quickly, their tolerance has changed. They become much, much more tolerant and less vulnerable. Fantastic, a potential management solution. So that part one, the conclusions of that is tolerance varies, but the most physically and most vulnerable. But most importantly, there is an option, and those most vulnerable species can become more tolerant if we manage them correctly. Part two of the presentation deals with the evil twin, the ocean acidification, the other carbon problem. And I'm not going to go into the chemistry, but what we're basically faced with is CO2 going in the atmosphere, going into the water, reducing seawater pH. And as Jennifer has said, that reducing pH basically reduces the amount of carbonate, the building blocks of coral that's available to coral in the water. And that's really important. These can have profound effects. They threaten the whole structure of a reef. According to the World Bank advisor, Thomas Lovejoy, the changes that we've seen in our ocean chemistry are 100 times faster than the last 20 million years. And you can see from the graph on the left-hand side there, it's a nice straight line and a big fat dip. These are really critical problems that we're facing. And that change in pH is directly related to the CO2 that we're putting into the atmosphere. That world map there from 2000 to 2099 shows things going from blue in the tropics to the greens. That green is not good for corals. Corals are going to be fighting hard to build their skeletons. This is a major problem, and it's occurring very, very rapidly. So our major consideration here was, how can we manage such a global event? Is it possible at all? What can we do about it? And we took two directions. What we did was look for natural systems today which raise the pH on a natural system because their biology drives that. We also tried to find those environments which were naturally today of lower pH. Will we find corals in there? And if they were, would they be adapted to the conditions that we'd expect to see in the future? A pre-adaptation, a new ecosystem service, if you like, a buffering for the natural pH increase and a pre-adaptation for the environments which have a low pH. Two habitats were identified, seagrass beds, and guess what? The mangrove systems. And the seagrass beds, we predicted that they have a buffering capacity, and the mangrove would have the pre-adaptation. So we went back out to Curios, and we mapped out the different habitats. The staff did the beautiful green seagrass beds, and the volunteers volunteered for the mangrove lagoon. That's the pitch I'm taking tonight anyway. And in those environments, we looked at the pH. The yellow there represents the open water signal. This is the status quo. This is what it should be like. The green represents seagrass. So you can see that there's an uplift in pH. And what you can see from this graph are the different colors underneath the dotted line. The reds represent when the environment is below the control, the yellow is the control, but the green is when conditions are above the control. That's the buffering capacity. When you do the mangrove, then we always see the line below the control. And the reds there demonstrate that the environment conditions in the mangrove is always below what we'd expect in the control. So they do actually represent an environment which is a bit of a window into the future, a natural experiment, if you like. The question is, of course, what happens to corals in the environment? In fact, can you see them at all? Now, if this was working, you'd see a nice video on the left-hand side of corals. And it's one of the most exciting eureka moments that we actually found. When the volunteers did drive by mutiny the staff into the mangrove systems, we were astonished to find not just the small corals, but the big, branching, architecturally complex corals. These corals living in waters of 34, 35 degrees, acid and pH environments of 2100, growing actively. These environments may be a bank of genetic biodiversity which could seed reefs of the future. When we looked at their growth rates, okay, yes, of course, corals don't grow so much quicker when they're in pH low environments. But they're surviving, they're hanging on. These environments are very important for the future of reef systems. And not just one type of coral, but every type of coral. Over 30 species of coral did we find in the mangrove during the 10 days that we studied there. So the conclusions of part 2. Corals can exist in pH environments which are present today that are predicted to be in the future, but they do at a cost. The question is, of course, will those reefs of the future sustain 1 billion people? Seagrass beds may buffer ocean acidification. Okay, but what I think we have demonstrated is that if you look into the extremes and you go past the norms and you push yourself and you have volunteers which push you on a daily basis, then you can start to discover some quite new things and unique things about our planet. Now, finally, what's the point of scientists doing all this research if it doesn't make a difference in society? And actually, over the last 100 years or so, scientists have never been really good at making a big difference in society. And that's where, of course, a volunteer organization like Earthwatch really is worth its weight in gold. It forces us to actually look at the research we do and try to make a difference and impact in society. And how do we do that? Well, there's 2 ways in which we can do that. There's the legal, policy, and management route, changing the way in which politicians view our planet and bringing our research into the political framework to make a difference. And of course, there's raising education awareness and getting the question out here, just like this seminar is doing, hopefully, for you tonight. In terms of the legal status, what are we doing in the Seychelles? Well, we're having a dual approach. We're focused at the national level, of course, and we're engaged through our social science team with the national management agencies, SMPA, and we're incorporating our ideas of these ecological refuge and these banks of genetic biodiversity into national plans. That's one of the points. But we're also working at an international level. Now, one of the unique things about Curious, because it has those mangroves and those feature environments, is actually they're just about the perfect underwater laboratory. Okay, and what we're trying to do, and we're in the motion of doing at the moment, is writing a proposal to UNESCO to make the marine park a biosphere reserve, to demonstrate a unique partnership between man and the environment, to use the knowledge that we've gained and the model of the corporate model and the NGO model with scientists to increase the environmental sustainability and the economic sustainability of marine parks. That UNESCO designation will have a positive feedback. Tourists visit this marine park, they pay to go there. That money pays for conservation. It all feeds in rather nicely, and we're very hopeful that we will have our name on that UNESCO Biosphere Reserve. In terms of the awareness and approach and outreach, well, of course, having volunteers. Not only do they help with the research, in terms of actually really helping. This year we had a team which was just absolutely outstanding. In fact, we couldn't keep them out the water. They were dragging us along half the time. They were fantastic. So not only do they do the research when we're there, of course, and bring new ideas and new experiences to the game, but we task them to make sure that they pass the message on to at least 5 individuals. And that snowballing effect increases awareness and knowledge. The participants on our social science team are funded by Mitsubishi as African Fellows, and they come from all conservation organizations across Africa. They come to learn from scientists in the field and take that information back to their own organizations about how research can inform policy, and that we're all committed to answer some of these big problems. The University of Seychelles is new. It's only been 3 years old. We've got the whole cohort of the University of Seychelles environmental degree joining our expeditions. The cover note there's only 3 of them. But still, we have 100% attendance at my lectures in the Seychelles. But what a great thing for us to do, this project to do, is to start to really enthuse a new university and graduates of that new university. It's very exciting. The socialization of the projects, the people are most important in the management, of course, it's their resources. We're visitors to the Seychelles. The social science team is communicating with local fishermen and users are participating in the design of the management, the design of the research. It's all as one. National media, this year we had TV interviews, we did a documentary and numerous radio interviews on Paradise FM, which is my new favorite. Internationally, we again did 2 documentaries, one for CNN this year, trying to get the message out there, and National Geographic, which to be honest is really down to Mitsubishi and Earthwatch driving those interests and relationships. National Geographic has been over with us 3 times, and of course, again, scientific publications. So with that, I leave you. I hope I haven't been too negative. It's a positive story. We can make a difference, and thank you very much for attending. Thank you.
Thanks very much, Dave. I'm sure you'll have plenty of questions that you want to ask associated with those 3 very stimulating talks. So we're now moving to a period of questions and answers. Just want to give you a few rules for those. I don't know if we're going to bring the lights up so we can see the audience a little bit more. But, firstly, please keep your questions related to the talks, nothing off-piste. Before you ask your question, please say who you are. Keep your question very short and to the point, not the long rambling intro, and say who the question is for, if it's someone specific or if it's for the whole panel. We've got hopefully 15-20 minutes for this, so I will try to get round the audience, but if anyone would like to start us off, please do put your hands up if you'd like to ask a question of the audience, of the panel. Yes, we've got one in the middle there.
Thank you. A question for Professor Smith about the the marine reserve in Hawaii. I was interested how the funding came about for that and how you got local buy-in, and whether you think that that's a model that could be used in other areas to help protect the reefs.
I missed a little bit about the beginning. Was it about the herbivore protection area?
Yes, in Maui.
Okay, yeah. So the
Thank you.
question was about how we got funding to do that project and whether there's any incentive to replicate that activity in other locations. So the project had, the protected area came into place after years of doing monitoring around the state. And that particular site was one that was really on the precipice of undergoing one of these phase shifts. So it still had a fair amount of coral cover, but there were macroalgae that were growing up around the corals, and we were worried that that reef was just on the edge. And it's one of the most popular dive sites on the island. It's a really easy place to get in the water. It's very accessible. And because of that, it's a place where many people learn to spearfish. And so there were virtually no herbivores left on that reef. And we believe that's why the reef was undergoing one of these shifts. In addition, that's also the location where the sewage is coming out that I also discussed. So it was kind of a double whammy, and it was just years of data showing that this reef was declining. And we had the fortune of working with the local state management agencies who, I remember at the time, asked me if we could make an herbivore protection area anywhere in the state of Hawaii, what reef would you do it on? And you know, they polled multiple people. It wasn't just me, but that particular reef was what I recommended, and that we were lucky enough to make that happen. I absolutely think that this is a management approach that should be replicated around the world, especially in areas where reefs are on the edge, you know, and it could also be used as a tool for reef restoration. If we can bring herbivores back to a certain population density, they can start potentially reversing these negative trajectories. So we hope to see it replicated elsewhere.
Thank you. Any other questions? Yes, over at the back here.
I had a question for Professor Huxham. I'm really impressed with the carbon credit work that you've done around mangroves. And I wondered if, like me, anyone was interested in whether there's an opportunity to offset some of my carbon through your project.
Thank you very much. I'll give you the bank account details afterwards. Actually, the biggest challenge, it's interesting that lots and lots of people are interested in this, partly because they see an opportunity for conservation in their areas, and partly because there's a lot of discussion in the scientific literature and elsewhere. But the real challenge, especially for a scientist like me, who's very naive when it comes to dealing with international financial flows, is dealing with the uncertainty in the carbon market. And it's been a bit of an eye-opener to discover just how fluctuating that is. There's no Swahili word for carbon. So trying to explain to our friends and colleagues in the village that, you know, I can't promise them that we'll sell all that carbon, and if we can sell it, it might be half the price that we sold last year, is a major challenge. So yes, we need to build up good relationships with people who are genuinely interested in offsetting their carbon. There's another element to that, of course, that some people might be doing it as kind of a moral excuse to avoid changing their lifestyles and other things. And that's an interesting political debate, but in my experience, there are plenty of people who take this very seriously and are looking for genuine opportunities for reducing carbon footprints that they can't do through changing behavior. So yes, happy to talk to you afterwards.
Any more questions from the audience? Yes, up here. Up here, okay. Can you shout?
Started studying marine about 15 years ago, and I just had a question for Professor Smith. Obviously, alternative livelihoods, fisheries, and seaweed growth has been obviously picked up quite a long time now, but that's the first time I've really seen it on the scale of, you know, shrimp farms in Thailand and stuff. I'm just unsure, what are the initial worries about what that kind of large-scale seaweed change in food flows because of the season, or would we expect that fish would come in and not necessarily be there? But how would we want to?
Yeah, that's a great question, and one that has largely motivated us to build this project, because there's really no data that exists on how those seaweed farms are affecting the surrounding ecology of the environment. We don't know. So most of the time these farms are planted over the top of seagrass beds, as I talked with some of you earlier tonight. And so whether they're killing the seagrass, thus reducing all of the juvenile habitat, so many small reef fish first settle into seagrass habitats when they're small and they grow up there and then they move out to the coral reef. If the seagrasses are no longer there, are the seaweeds providing the same service for those fish? Are they recruiting into those beds or not? Are they sequestering the same amount of carbon that seagrasses do, which we also know they're quite good at? So there are a lot of questions that we don't know. And again, because the scale of these farms has increased so rapidly over the last several years, we need to get these answers. So I don't promise to get all the answers myself. We need a large team of people addressing this issue because it's occurring not just in Indonesia, but Eastern Africa and the Philippines and many other small tropical island nations. But yeah, great question.
Thank you, Jennifer. Next question, from the top or bottom? Yes, the lady here.
I was just wondering if there's a particular reason for mangrove destruction or mangrove loss in the area that you're working in. And if there is there any work to reduce this particular impact?
Thank you. Yeah, the largest cause of mangrove destruction, the largest single cause of mangrove destruction globally is still shrimp farming. And I think Martin referred to that. So try and avoid those tiger shrimps. But most of that occurs in Asia. So about 40% of mangrove loss over the last 30 years has been driven by shrimp farming. In East Africa, that's not the main cause of loss. We know that we lose about somewhere between 0.7 and 1% of the mangroves in Kenya over the last 20 years. That's been the rate of loss. And most of that is driven by that dependency from necessity, as I called it. So it's driven by poverty. It's expanding populations, people relying on those forests for fuel wood and for timber, and some poaching as well. So the forests belong to the government, and it's actually illegal, or until recently it was illegal to take wood from the forest. Now you can do that with a license, but management is a significant problem. So the only way around that in East Africa is to really engage local communities in the way that we're trying to do. It's a very interesting question why shrimp farming continues to destroy mangroves elsewhere, and it's mostly to do with the rich and powerful making money, making a quick buck, and leaving local people with a devastated landscape.
Yes, over there in the corner.
Hi, James Burrell from Queen Mary University. So we're quite familiar with sort of tropical forests and how long they might take to regenerate, for forests to come back, perhaps tropical forests 100 years or something like that. In the context of mangroves, if you had an area that was cleared, how long might it take to regenerate a fully functioning mangrove ecosystem? Perhaps whoever thinks they're best placed to answer.
Well, one of the first questions that we asked when we first arrived in Ghazi was whether it was possible to restore degraded areas of mangroves. And these were two areas in particular close to the village where there'd been an extensive forest, and the forest had been removed for industrial purposes, probably as a tax break or illegally, many years before, about 35 years before, and there'd been absolutely no regeneration in those areas. And we had no idea whether we'd be able to restore those areas. And one of the real benefits of working with Earthwatch is that they're an organization that are willing to take a chance on that kind of speculative science. So it's a long-term project. These trees grow quite slowly, at least in that site. And we really didn't know if it would work at all. And what we discovered was that once you remove the trees, there are all sorts of chemical changes in the sediment. In particular, there's deposition of salt. So the simplest mechanism is that you get very intense sunshine, that evaporates seawater and it leaves lots and lots of salt. So you end up with these salt pans where nothing can grow, and you can reverse that if you spend a lot of time nurturing trees and planting them in nurseries and getting them through critical phases in their life stage. So that original experiment that was started about 12 years ago, now we can't run the experiment anymore because it's been so successful in reseeding our control areas that we don't have an experiment anymore. So in answer, that kind of area, you can restore it, but it takes a long time. If the area isn't changed chemically in that way, then mangroves can grow extremely fast. So they can grow more than 1 meter a year in productive, good areas. So they're very resilient and they can recover very fast.
Well, I'll indulge in a follow-up question actually for the rest of the panel, I think. There's clearly very strong connections between mangroves and corals in terms of fish recruitment and protection from terrestrial runoff. Have any of the other members of the panel seen any evidence of clear degradation of coral reefs because we've lost the mangroves rather than because of any other impact?
Well, yeah, I certainly have. If I just jump in there. One of our other sites actually in Indonesia, and there the use of mangrove is pretty dramatic. It's harvested. It's not actually removed too much. It's more coppiced actually, but there still is significant degradation, and what we basically see is a cascade effect. We find that sediments erode, sediments stop getting entrapped. Any sediment or pollution coming from land doesn't get trapped. The seagrasses next to that mangrove get degraded, and finally that sediment and degradation occurs on the coral reef. Let me give you some numbers. In that area, coral cover is maybe 50%, where the mangrove's degraded, it's down to about 20%, with probably fish biomass reduced about the same. So from my perspective, one of the first things we do when we're looking at reefs is look at the connectivity and the connected systems. A healthy mangrove, healthy seagrass usually means a healthy reef.
We've got time for one more question, I think. We've got two. We'll go for both. We could fit two in. Gentleman at the back there first, and then we'll have one more question from here.
Hi, Benjamin Coburn from the University of Oxford. Mine was actually on the Twitter, but I forgot to use the hashtag, so I'm just going to ask it. The most shocking slide to me today was actually in Professor Huxham's presentation, where he showed, the human rights, environmental issues, and all those are crossed out, and the only language that we speak is money. Now, I'm not saying that I think that's the way you think, but how do we actually address that as a fundamental question? And I know we don't actually have the answers to that. I'd just like to hear some of the thoughts on the panel on that, because something like carbon credits for mangroves sounds like a nice idea, but it's incredibly difficult in what, a Kenyan situation that's pre-capitalist in some ways, but then another situation like in Hawaii where you've got a dive industry, so there's direct support for doing something like herbivore reduction. So just some thoughts from the panel on that issue of money and human rights and environmental issues.
If we can make the comments quite quick.
Yeah, so of course
it's get the questions in.
Deliberately provocative slide, I know. I think part of the answer to that is to try and distinguish between those values that are genuinely distorted by expressing them in monetary terms, and those values where it's useful to translate them into money. And values which are already marketed, commodities that are already marketed, but which aren't properly captured by the market, and actually fuelwood and some of the fisheries products of mangroves and other places, I think that's helpful because it's making the market work better. Values such as the intrinsic worth of ecosystems and perhaps the intrinsic worth of life, including human life, when economists start putting money on those values, that's much more controversial. But that's a big debate.
And certainly with coral reefs, we've had global economic valuations done, and in places like the state of Hawaii, one of the single largest sources of revenue is tourism, and so we should be investing more resources and energy into protecting those environments. Of course, to do that, it also requires money, and so that's where the disconnect and the fight somehow comes out. So we're trying to provide, as scientists, the evidence that more needs more time, more money needs to be invested into protecting these resources. Some of it comes down to just proper management. For example, you don't need a fishing license to go fishing in Hawaii, and so anybody can go fish whenever. And so therefore there's not the revenue that's going back into the fisheries, right? So doing simple things like changing some fisheries regulations could help largely.
I slightly lied there. We've got 2 more questions. We've got one from our online audience. I'd like to take one question from our online audience. If you'd like to read out the question, please.
Yeah, thank you, Martin. Yeah, we've got a question from Jenny House, who's with a group of friends at New York University master's program, and they're having a dinner party and watching the live stream online. So they've posed a question: what should the balance be between community-based conservation and government top-down policy? So what should the balance be between community-based conservation and government top-down policy?
Okay, I guess it depends on the case study, but perhaps the panel would like to suggest that.
I hope they've been enjoying their party.
I think they're in a tutorial, actually. It's probably,
it's quite early for a party, isn't it? Anyway, welcome to the talks. It's a very difficult question. I think the balance depends on the society you're working. I wish, in a sense, that all conservation could be bottom up and it would emerge from discussions, but from our experience that you do need to have rules and regulations, and rules and regulations need to have some level of enforcement, particularly when conservation starts. So I'm sorry to sit on the fence, but I think there needs to be rules and regulations, which is a top-down approach, but those rules and regulations require the input from the local community and some meeting in the middle.
And I think another important angle to that, I think, is that I think if you look at the top-down government side of things, they could do much more to actually support the community initiatives. A lot of the answers come from the community, and they struggle with resources, they struggle with bylaws or wider laws to actually instigate what they want to do. So I think one thing they can do is actually support the local communities much more, because it doesn't necessarily, people in the central government don't necessarily have the right answers. So I think we'll take that last final question just here if we can.
Yes, hi. My name is Trevor Moss. I'm a member of the Scientific Exploration Society. I'd like to ask Emily Penn a question. I was watching or stumbled across a video on YouTube last week, and it was a Japanese inventor that had created some equipment to convert waste plastic back into oil. And he was promoting this particular invention, specifically in relation to small island projects. It seemed such a great idea to me. I wasn't sure whether it was a spoof or not, but I just wondered if you'd come across that, or whether that is reality.
Yeah, great question. I think, you know, it is a reality. There's some brilliant technology out there that's turning waste into energy. The one you mentioned, definitely turning it into oil to use as a fuel. There's other technology called plasma gasification, which is essentially gasifying anything. It can be plastic, it could be organic, and turning that into energy as well, and also tapping off gases and metals. So lots of very interesting ways to deal with waste. For me, though, at the end of the day, it always comes back down to our planet works in circles. You know, we have cycles, and for us to develop sustainable systems as human beings on this planet, we need to develop systems that work in closed circles, a circular economy. And as brilliant as those waste to energy solutions are short term at dealing with the waste problem, they're not real long-term solutions, because they will never be closed loop. So a lot of the solutions that we're trying to work on is how do we completely close that loop? How do we remove single-use plastic from our waste stream altogether, so that we don't have that waste at all, and we're no longer taking that oil from the ground, and eventually it will end up in one form or another as CO2 in the atmosphere and other waste products.
Thank you, Emily. Okay, well, thank you for the questions. It's now my job just to close the meeting with a few final thoughts and perhaps where we're going. So I think we just need to switch the slides over. Thank you very much. Okay, so where are we with marine conservation? This diagram shows the trend in the global designation of marine protected areas around the world in terms of area. And we have this global commitment to have 10% of our seas actually designated and protected. The green line is where we are with terrestrial area, so you can see that a large proportion of the terrestrial environment is protected. The blue one is the marine environment. You can see for quite a long period of time not much was happening, but what we have is a very steep increase in the number of protected areas, the area that's been protected in recent years, and this looks very positive. But how is this made up? Well, a large reason for this recent leap in areas is the designation of some of these very large marine protected areas that have been mentioned today. We've mentioned the ones in off the Pacific, Hawaii Islands, etc. We've very recently, the UK has designated, or in the process designated, Pitcairn. So a large proportion of this percentage area is due to these very large and very important designations, which are protecting some of these vital, undamaged systems that Jennifer talked about so extensively. But could these actually be defined as low-hanging fruit? It's very simple in some ways for a government like the UK to designate a far distant Indian Ocean or Pacific Ocean area, very important though it is, and perhaps not necessarily concentrate on what's really important in terms of how we conserve our busy coasts, where most of the damage has occurred and most of the activity is going on. Can we make a difference to these areas? Well, it might not be so exotic, but a fine example of success in this sort of area is from the Lyme Bay study, which we are involved with, amongst many others, down in the southwest of England. And this is all down to partnerships. And I think one of the things that have come from all these talks is partnerships are absolutely crucial to any success in protecting our coastal environment. And this partnership involves fishermen, it involves fishermen enforcement, fisheries people, scientists, conservation bodies, and we're all sitting around the same table, and we've all got a common aim, and that's for sustainable seas and a sustainable fishing industry. And I think that holds true for wherever we go in the world. In 2008, a 200 square kilometer marine protected area was designated, excluding trawling and dredging from the seabed, but allowing all other fishing, which is the majority of the small boat fishermen using static nets, lobster pots, etc. And what we've been doing is looking at success in terms of the recovery of the seabed, and it's an indicator of what can happen in many of these coastal protected areas. And what you can see is even though there's a successful fishery going on, we are still seeing major improvements because we are focusing on the key damaging activities. And this just shows the trend in species richness, the diversity of the seabed, these lovely reefs that we've got off the south coast of England, which most people don't even know they're there. We've got our own coral reefs, they're fantastic. But see, it's taken 3 years before you even see any change. This is not an easy win. And sometimes that puts off sponsors, puts off funders because they can't get a really quick win. And some protected areas that have been particularly damaged, as we've heard from mangroves, can take a long time to recover. But that shouldn't put us off doing what we want to do. But we need to feed people from the sea as well. We can't just fence the environment off and keep people away. So how do we move forward? Do we need some new thinking in the way we use our sea? And it's quite interesting to compare our concept of what goes on in land historically with what goes on in sea. And this is two pictures from the terrestrial environment we're very familiar with and very happy with. The top one was a national park, Dartmoor in this case, because it's down the southwest. I have to plug the southwest. And we love our national parks. We treasure our national parks. We love visiting them. We're really comfortable with that level of protection of our environment. We still utilize them, but in a very managed way. But we also have scenes like this in the UK, where we're producing food very intensively. There's absolutely nothing natural about that scene at all. But we're happy with some of our environment to be used to produce food. So should we be thinking of the marine environment in the same way? The ocean has traditionally been a free-for-all. We don't allow farmers a free-for-all in the terrestrial environment. So do we need to think of a different way of looking at our marine environment so that we have really valued protected areas, national parks in our seas in different countries, but then look at how we can really generate intensive food production from other parts of our ocean, just like we do on land. It's something that we need to think about for the future and things that we've been talking about for a while. So if we're talking about the future, I just want to end with this, which a lot of people in the general election might have missed. This is actually a quote from the Conservative Manifesto. And for those who don't know, the Conservatives made the biggest commitment to marine protection out of any of the parties at this recent general election. And you can see from this a couple of things. They are going to go further and create a blue belt around the UK's 14 overseas territories. And they're also going to complete the network of marine conservation zones around the UK. This is the commitment they've made for the next 5 years, so it's our job to make sure we hold them to that task, which is hidden away and not really mentioned in the media much at all. It's there written in their policy. But to bring us to a conclusion, we can pick a couple of words from this, and this says it all. You know, we will designate subject to local support, subject to the views of the local community. And this is what it's all about. It's all about this partnership. Humans are an integral part of the coastal ecosystem, and we mustn't forget that. We're not separate from it. We're not a different animal that doesn't interact with the environment. We are part of it. We can't fence these sort of environments off and keep people away. We need to work with local communities, not exclude them or try to tell them what to do, which is often the case as we move into developing nations in the tropics. We can make a difference. We've heard today that we can actually recover systems if we manage to remove some of the worst of the damaging activities, and it does make them more resilient to some of these global changes that perhaps we can do very little about, but the systems themselves may be able to deal with. It's an old adage to think global but act local. And this is something we have to do more than anything in marine conservation. We can all make a difference. And Earthwatch particularly is very much a part of the solution, as we've heard tonight. I'd like to thank you all then. Firstly, the speakers. I think we deserve a great round of applause for the speakers. On behalf of Earthwatch, I'd also like to thank the sponsor of these events, which is the Mitsubishi Corporation Fund for Europe and Africa. Thank you very much to them. Thank you to the audience in the room for joining us, and also those of you across the globe, including Jenny and her friends in New York. Thank you for joining us in the live feed and on Twitter. We have, I think, an advert here. The next, I'm pleased to announce that the next Earthwatch event will be on the 29th of October here at the RGS. And this is the annual debate for Earthwatch. The team are currently discussing topics, but we'd like your input. What would you like to discuss? What would you like to talk about? And please send your ideas to #EWDebate, and we will add them into the mix in terms of the decision of what we're going to do. Now, perhaps importantly, the speakers will be going to the bar for a well-earned refreshment after this. So please join us for a drink if you have any more questions or would like to talk to the speakers further. We'll be there for a little while. You go out through the main auditorium doors, which are those ones, I believe. Yeah, go out there and turn right. So thank you all once again. Final thank you to the speakers, and I hope you had a very good evening. Good night.
Well, I think we're going to the bar. We can probably, if you want to go back to the room, it's that way. The bar's up.
Oh, is it? Okay.
It's the map.